Okay, geometry, we're going to take a very quick tour here through what was going on in section 2.6. But I do need to clarify here, we are not actually formally covering chapter 2 this year. We're just taking the time right now to really talk about one theorem that does get presented in section 2.6 that actually ties in better with what we're doing right now at the end of chapter 1. So most of this section now we're going to skip, and this is actually a very short section of notes. So the first thing we're going to do is talk about theorem 2.1. Now, if we've missed this before, and I don't know that we've had a chance to formally discuss it, I want to talk for just a second about what this word means, because I don't know that we've had a chance to define it yet. But you can't really understand the meaning of the word theorem unless we also go back and talk about the meaning of the word postulate. These two words exist hand in geometry, and you can't know one unless you really know the other. So a postulate, everybody, is a mathematical statement. Okay, basically it's a rule or a law known to be true. So this is important, known to be true. But now I'm going to switch to red. This is important, that cannot be proven. Okay, now proven is an important word in geometry. It's built off that word proof, which is actually what we normally spend most of chapter 2 talking about. Being able to prove something true is kind of the fundamental idea of what we do really in all of mathematics, but especially in geometry. With doing remote learning this year, we just decided that it would be a bad thing to try to cover with you guys remotely, so we're not doing much with it. But this is the formal definition of a postulate, a mathematical statement known to be true that cannot be proven. Now, the difference between a postulate and a theorem is really just this red statement underneath here. So give me just a second. When I go to define what a theorem is, let me actually group these two things together right now, and then let me go ahead and clone them, because this definition right here for theorem starts off the exact same way as postulate. A theorem is, again, a mathematical statement known to be true, but the difference here now is that a theorem that has been proven. That's the difference right there, okay? That someone has taken the time. We'll go ahead and underline all that. Somebody has taken the time to say, I know this is true, and here's how I know it, and it works in every single case that satisfies the hypothesis of that theorem. So a postulate is something usually that's so basic that every mathematician in the world looks at it and goes, yeah, that's true. We don't really know why. Very often it's self-evident. So an example of a postulate, you guys, is like one of Euclid's basic ideas that says that if you've got 2 points, A and B, there is only one line that passes through both of those points, and we would define that as line AB. There's not a second line, there's not a third line, there's only one. That's a statement that everyone can look at and know that it's true, but it defies the concept of formal proof because it's so basic, because it's so obvious. Now, an example of a theorem, however, would be something, well, let's go with the one that you guys know more than any other theorem out there, the Pythagorean theorem. A squared plus b squared is equal to c squared, which we got to be careful, only works in certain circumstances. It only works if your triangle is a right triangle, and it only works if A and B are the lengths of the two legs and C is the length of your hypotenuse. That's what I mean about the hypothesis of a theorem, everybody. Certain things have to happen, but if they do, this theorem right here always works out. A squared plus b squared equals c squared. Now, I don't know the exact number, but there are multiple commonly accepted proofs of the Pythagorean theorem. In fact, one of my favorite stories right here, a U.S. president, and I want to say it was James Garfield, but I'm actually not sure, was actually a mathematician and submitted his own proof of the Pythagorean theorem, different from what anybody else in thousands of years before him had done, and got that one published as well. A theorem, we know it's true, and we can explain why. Now, I haven't explained why for this one to you guys yet because, frankly, we don't have the mathematical tools in the arsenal right now to be able to understand and why the Pythagorean theorem is true. But when we get to this in chapter 7, it'll have something to do with drawing what's called an altitude from the right angle to the hypotenuse, and then realizing that your hypotenuse got cut up into two pieces, x and y, that altitude has a length that we usually call h. And then there's a ratio that's always going to be formed here, guys, that the ratio of, let's see if I remember this right, x to h ends up being the same as the ratio then from h to y, and we can use that concept there to prove the Pythagorean theorem. I'm not going to bore you with how to do that right now, but I'm just going to ask you to trust me there that there is a proof for the Pythagorean theorem and for every theorem out there. So this is the main difference between a postulate and a theorem. So back to this, guys. Theorem 2.1. It's called a theorem because it has been proven. It is numbered in your book Theorem 2.1 because it came from chapter 2, everybody, and this is the very first theorem that your authors chose to put in this chapter. Now, one thing we should be very clear on, everybody, if you were studying from a different geometry book this year, or if you have a friend at a different school who's using a different geometry book, this might not be Theorem 2.1 in their book. It might have a totally different number. That book might not have numbered the theorems at all. Okay, so the number is different from book to book, but the concept is the same. This one is called the vertical angles theorem, and if you recall, we talked about what vertical angles were back in section 1.5, if I'm not mistaken. So vertical angles were two non-adjacent angles that were formed by intersecting lines. So I'm going to draw one line here, and then another line that crosses it. So we've got two lines crossing there with this one point of intersection right there. And what we said then is that when you intersect two lines, you are going to form four angles. And I'm just going to number them quickly, 1, 2, 3, and 4. And in section 1.5, we defined vertical angles to be two non-adjacent angles formed by these intersecting lines. Remember that adjacent means next to. So if we were going to focus on what was happening right here in angle 1 up on the top, the adjacent angles to angle 1 are the ones right next to it. That would be 2 and 4. 2 and 4 are adjacent to 1, and that leaves angle 3 down here on the bottom as the only non-adjacent angle. And now this theorem says what I think a lot of you guys know already, that vertical angles are congruent. So if angle 1 and angle 3 are vertical angles, this theorem tells us that those two angles have to be congruent. So that's why I waited so long to put a second arc mark down in angle 3. Those arc marks indicate that they're congruent. This is the exact same piece of information, but it's written in a format that most of our theorems and postulates are written in, and it's called if-then form. Here's the if, there's a comma, and then here's the then. The if part of an if-then statement establishes the hypothesis. It kind of paints the picture, makes the setting right here of what's going on. If two angles are vertical angles, well, that's what we have in this diagram with angle 1 and angle 3, and then at that point we can read the conclusion, then they are congruent. And of course the same thing happens over here with angle 4 on the left and its vertical angle, which is angle 2. So I did a double tick mark for both. Now, very quickly, I'm not going to spend much time on this, the reason this is a theorem and not a postulate is because it can be proven. And let's talk very quickly about what this would mean. So let me actually go with the same setup, 1, 2, 3, and 4, and there we go. All right, now what we do know here, guys, from the diagram is that angles 1 and 2 form a linear pair. We are allowed to assume that from the diagram. So 1 and 2 form a linear pair, and a postulate that we learned back in section 1.5 was called the linear pair postulate. It said that if two angles form a linear pair, then they are supplementary. So if I was making a list of things that I know, I would start off by saying angle 1 and angle 2 form a linear pair. I'm just abbreviating here, guys. Then I would say that angle 1 and angle 2 are supplementary. That's by the linear pair postulate. That means they add up to 180 degrees. But of course, the exact same thing happens with angle 2 and angle 3. I could also say that angle 2 and angle 3 form a linear pair as well. And I could also conclude then that angle 2 and angle 3 are supplementary to one another. So let me break from formality and just go with something numerical. This is not really the way to do a proof, guys, but let me just say for the sake of argument that the measure of angle 1 is 50 degrees. Now, since angle 1 and angle 2 form a linear pair, meaning together they make a straight line, we know that those angles have to be supplementary, so they add up to 180 degrees. So, if I already know that 1 is 50, to find the measure of angle 2, I would just take 180 minus the one angle that I know and get 130 degrees for the measure of angle 2. Then, if I go and look at these two facts, 2 and 3 form a linear pair, right? Because that's a straight line right there. That makes 2 and 3 supplementary. So if I know the measure of angle 2, I can find the measure of angle 3 by taking 180, subtracting the 130 from that, and that gets me right back to 50 degrees here, which matches where we started up here for angle 1. And guess what? I could do it again now for angle 3 and angle 4 and take 180 minus the 50 degree angle, which I already did, and get 130 degrees here for the measure of angle 4. So sure enough, that proves that these two vertical angles are congruent as well. All right, so with that in mind, guys, we've got that written down. We are not going to formally prove this theorem, so don't worry about that, but I do want to do this one example with you, and then we're done, everybody. So we're going to find x and y, and you guys know I like you to check your work, so we're also going to find the measure of each angle in this problem. So what were we given? Well, we can tell from the diagram that we have two lines and that they intersect at this one point right here, and that creates 4 angles. And anytime you've got that, you do have linear pairs, but what's probably easier to deal with is the fact that we have vertical angles. I've got this angle, the 7x plus 4 degree angle, in the upper left-hand corner of this intersection. The one across from it, its vertical angle, everybody, whoa, I didn't want that to happen. Its vertical angle would be in the lower right-hand corner, this one right here. Those are vertical angles. We're allowed to assume that from the diagram, and the theorem we just learned said that vertical angles are congruent. And once again, the word congruent in geometry means having equal measures. So the 7x plus 4 degree angle has to be equal to the 10x minus 29 degree angle. They are vertical angles, we know they're congruent, and congruent means having equal measure. So this one wouldn't be too bad to solve. I would subtract a 7x from both sides, while at the same time adding a 29. 7x's on the left cancel, 29's on the right cancel. 4 plus 29 is 33. 10x minus 7x is going to be 3x, and we would divide by 3 now and get x is equal to 11. And that was one of the things we were asked to do here, was to find x, and we've got that one done. The other thing they wanted us to do now was to find y. All right, so once again now, just looking at it a slightly different way, we've got an angle in the top right corner and an angle in the bottom left corner. Those are vertical angles, and vertical angles must be congruent. So I'll take one of them, 12y minus 9, and set that equal to the other of 126 minus 3y. Now from here, let's take a look, guys. I would add a 3y on both sides, and at the same time move the constants to the right by adding a 9. 3y's on the right cancel, 9's on the left cancel. 12y plus 3y is 15y. That gets us 135 on the right, and dividing by 15 on both sides, I'm pretty sure is going to get us y is equal to 9. So okay, everybody, we found the values of both x and y. Now we're going to do the measure of each angle just by substituting in. We know now, or we believe, that x is 11. 7 times 11 plus 4, you should really be doing that in one big step in your calculator, is going to get you an 81 degree angle right here. Let's see what happens on the right, bottom right. 10 times 11 is 110, and 110 minus 29, sure enough, is 81 degrees as well. And it should not surprise you that those two vertical angles are congruent. Now, let's keep going with this, everybody. Now that we know that y is 9, let's plug that in here. 12 times 9 is 108, and 108 minus 9 is going to get you 99 degrees. Now let me stop right there and say that I haven't found the measure of the other red angle yet, but I do feel pretty good, you guys, because these two angles here together, 81 and 99, happen to add up to the magic number of 180. You've got a straight line coming right across the figure, which means these two angles form a linear pair. They have to be supplementary. They have to add up to 180, and they do. So the only thing left to do is this piece right here, guys. So 126 minus 3 times 9, again, that's really a one-step operation right there in your calculator, everybody. 126 minus 3, and it's not a bad idea to use parentheses here, or you could just do times, but sure enough, that gets us 99 degrees as well. So the two things I would want to check are, number one, are your vertical angles congruent? I think so, everybody. 80, whoa, that was weird. 81 and 81, those are the same. And also a 99 and a 99, those are the same. And the second thing to test here, are your adjacent angles going to be supplementary? And we've got an 81 here and a 99, and those two do add up to 180. All right, guys, that's as much as we were going to do from section 2.6. Really just knowing that vertical angles theorem and how to use it is all we had to cover from here. So good luck, everybody, and let me know if you have any questions on the homework.